I welcome this opportunity to present a film which will show you the status and some of the major milestones which we have passed in our Air Force ballistic missile program. As we see it, our job is to help our country and the whole free world to build deterrent power sufficiently persuasive to prevent outbreaks which would lead to global war, to buy the time for working out conditions of peace by diplomatic, economic, political, psychological, and other means, for the underlying purpose of a free people's military strength is to safeguard life and not to destroy it. The perils against which we must gird ourselves become more complex and many-sided than the risks assumed by the aggressor. He has, as a rule, the prerogative of initiative. He can concentrate more narrowly upon the choice of targets and upon the use of weapons which seem to hold the highest promise of victory. But a country such as ours imposes upon itself the need to prepare against a far wider range of military contingencies. Whatever the form of our deterrent power, we must never forget that the Russians have been emphasizing since the end of World War II the decisive importance of the new science and technology as applied to weapon systems. The Sputnik and Lunik are cogent proof of Soviet progress in this area. It is in this context that I would like to show you some of the work we are doing in our Air Force Ballistic Missile Division. In addition to the Thor Intermediate Range Ballistic Missile and the Atlas, Titan, and Minuteman Intercontinental Range Ballistic Missiles, we have also been conducting programs for the Advanced Research Projects Agency of the Department of Defense and the National Aeronautics and Space Administration.
Of the Air Force Ballistic Missile Program, the most far-reaching military development program ever undertaken in our history. This is the story of how the American people are building a new power for peace. Toward the end of World War II, Germany demonstrated the possibilities of the ballistic missile by firing some 300 V-2 rockets from continental Europe into London and its suburbs. The V-2's guidance was crude. Its payload, the bomb it carried, was deadly, but limited in size and power. The maximum range was 200 miles. For its time, though, the V-2 was grimly efficient, and it was the forerunner of today's long-range ballistic missiles. What is a ballistic missile? Actually, it's a bullet, a big one, propelled and guided to a point in space from which it proceeds along a free-flight trajectory until it re-enters the Earth's atmosphere and falls on its target. It is composed essentially of four major portions, or subsystems. The nose cone subsystem contains the warhead, a nuclear bomb. The guidance subsystem keeps the missile on course during the powered portion of flight. The airframe subsystem is made up mostly of fuel and oxidizer tanks. The propulsion subsystem contains the rocket engines which boost the missile to a speed of thousands of miles per hour. Looking more closely at the principle of the ballistic missile, we can readily compare it to many weapons in use throughout history, even with something as relatively simple as a bow and arrow. The thrust of the rocket engine, which supplies the missile's propulsion power, may be likened to the force of a flexed bow, which propels the arrow into free flight. Guidance is possible only during the brief period when power is applied. When that period ends, the arrow, or missile, must have the right combination of position, speed, and direction if it is to hit the target. For the ballistic missile, the end of this guided period can be one of many points in space and occurs when the engine stops and the nose cone separates to follow its ballistic trajectory to its place of impact. During almost all of its ballistic trajectory, the missile is above the Earth's atmosphere in the vacuum of outer space, unaffected by external forces other than gravity, until it re-enters the Earth's atmosphere a comparatively short distance from the target. Operation of a multi-stage, long-range ballistic is essentially the same as the single-stage variety. The stages are coupled. Each stage has its own rocket engine. The first stage engines are ignited on the launch stand and boost the missile along a flight path, straight up. The missile's guidance system starts controls, and the vehicle makes a turn in the direction of the target. The first stage power package burns out. Then the second stage engines start, boosting the second stage to the required speed. Finally, at second stage engine burnout, the nose cone separation occurs, and the payload is then in free ballistic flight to the target at some 15,000 miles per hour. Thus, the ballistic missile is a long-range weapon operating at tremendous speeds, a weapon capable of delivering a devastating nuclear payload in half an hour to practically any place in the world. Our military requirement after World War II was this: could we develop a ballistic missile large enough to deliver a huge atomic bomb 5,500 nautical miles or more? Under Air Force direction, design work began on such a gigantic missile as early as 1945. To carry the early, extremely heavy atomic bomb such a distance required a missile of tremendous weight. The solutions, which at first seemed possible, proved to be impractical from both a military and an economic standpoint. Then came the thermonuclear breakthrough of 1953, which made it possible to build a bomb with very high destructive power, yet relatively low in weight. Following the recommendations of the newly formed Air Force Strategic Missiles Evaluation Committee, under the chairmanship of the late Dr. John von Neumann, as well as the suggestions of other top scientific and military figures, the Air Force, in May 1954, assigned highest priority to ballistic missile development. Schedules for development, test, and production of ballistic missiles were set up, and although these schedules were admittedly optimistic, they were all met, some of them far faster than was thought possible. In an unpretentious former parish schoolhouse, contrasting sharply with the magnitude of the job that lay ahead, the men charged with the responsibility for developing the Air Force's ballistic missiles set up their headquarters. By August 1954, the Air Research and Development Command organized and put into operation what is now the Ballistic Missile Division, which mobilized scientific and engineering talent, military skills, and industrial initiative to a degree never before equaled in any single program. Only a little more than 4 years later, more than 90,000 individuals were members of a science, industry, government team, representing a cross-section of our country's human and material resources. Space Technology Laboratories was chosen to provide systems engineering and technical direction for the Air Force Ballistic Missile Program. The Ballistic Missile Center of the Air Materiel Command was formed to handle procurement, production, and logistic support for the program. The Strategic Air Command soon became a member of the team, training crews and helping coordinate the tasks of operating the missiles in the field. Working closely together in a central headquarters in Inglewood, California, this unique management organization has directed an accelerated program of weapon system development. Traditionally, such programs have been marked by periods of study, development, test, production, personnel training, and introduction into weapon inventory, all of which take place in a series of steps or stops, one following the other, covering a period of from 8 to 12 years. By means of the management concept of concurrence, which means moving ahead with everything and everybody, all together and all at once, we have been able to compress the time required for weapon system development. We have been able to reduce its time from 8 to 12 years to 3 to 5 years. In the program control room, nerve center of the Ballistic Missile Division, the schedule status of every detail of all projects, large and small, is on the record. To help carry out the ballistic missile programs, industry has built a vast complex of facilities for development and testing of everything from the smallest part to the entire missile. In 1954, only Convair and North American Aviation were involved in ballistic missile development. Today, there are 30 principal contractors, over 200 subcontractors, more than 200,000 suppliers. These are some of the facilities in which ballistic missile ideas are translated into the reality of hardware. Many of these manufacturing and assembly plants are new, built especially for the ballistic missile program. In other cases, existing plants were quickly modified to take on their new ballistic missile assignment. To turn out ballistic missile subsystems requires engineering methods never before used in weapon system production. The urgency of the program demanded new, bold methods for applying engineering theory to manufacturing problems. In many cases, new machine tools and equipment had to be created. New plant layouts had to be designed. New materials had to be found and applied. As a result, manufacturing organizations have been able to handle with great speed the large number of production changes resulting from the experimental nature of a development test program, all phases of which are carried on simultaneously. The major aims of such a concurrent development test program are to provide necessary information at the earliest possible date and to reduce the number of costly missile flight tests. This concept may be represented by a pyramid, which forms a broad base of parts and components testing, followed by subsystems tests, then captive tests of entire missiles, and finally, flight tests. Beginning with the smallest parts first helps to minimize the possibility that the entire missile might fail because of a failure in an individual part. The nose cone test program demonstrates this pyramid test concept. Small parts which are to go into the nose cone are subjected to shaker table and other rigorous tests. Artificial flight conditions are simulated in the laboratory. Shock tubes and wind tunnels help solve special problems. For instance, will a particular nose cone skin successfully survive re-entry into the Earth's atmosphere at extreme speeds? Full-scale re-entry vehicle drop tests are also conducted. After a period of free fall, nose cones are rocket boosted to intercontinental ballistic missile re-entry conditions. Special experiments have been conducted to solve particularly difficult problems of re-entry. Three-stage rockets, for example, were used to carry a variety of nose cone designs above the stratosphere and propel them back to Earth at speeds as high as 15 times the speed of sound. This experiment confirmed theories about re-entry conditions. Further research produced a new type of nose cone, the ablation type, which uses the principle of controlled melting of the nose cone shield during re-entry. And finally, the Thor-Able Advanced Re-Entry Vehicle tested and proved the ablation-type nose cone design in flight tests of over 5,000 miles. Propulsion subsystem testing provides another example of the ballistic missile test philosophy in action. Special stands permit checkouts of rocket engines and their fuel systems. Still other and larger stands in contractors' backyard test facilities accommodate captive tests of complete missiles. Captive firings, with the entire missile held secure, make possible study and analysis of the whole missile system under conditions approaching as closely as possible those of actual flight. Flight test facilities for the ballistic missile program were built at Cape Canaveral, Florida, and on the stations of the Atlantic Missile Range. Engineering and test personnel, representing nearly all of the contractors in the program, occupy hangar buildings at the Cape. After arriving at the hangar area, the test missiles are subjected to inspection and checkouts, designed to guarantee their readiness for the payoff of the test program, flight. The entire 5,000 miles of the missile range from Cape Canaveral to Ascension Island is studded with highly instrumented tracking stations serving all military services and all types of missiles, and gathering continuous flight test data on missile performance. Many of the islands are owned by Great Britain. Permission to install tracking stations was obtained through negotiations with the British government. Similar agreements have been made with the Dominican Republic and Brazil. The island installations are basically quite similar. They vary in detail only in their particular assignment. The Atlantic Missile Range Facility also includes search planes and vessels. Their function is to record terminal flight data, locate impact points, and to recover the data capsules carried in the nose cones of most long-range missiles. The second Thor flight test was conducted only a little more than a year after the first Thor contract was signed. All instrumentation showed that the missile was on course, except the range safety officer's tracking display board, which showed the missile was heading inland instead of out to sea. The safety officer had no choice. He had to destroy the missile. Investigation revealed that electrical wiring to his display board was reversed, thus relaying faulty information. Shortly afterward, this Thor missile achieved all flight test objectives. The flight was regarded as an unqualified success, and one of the outstanding aspects of the test, that it occurred less than 18 months after the Thor program was first authorized. This Atlas on its launch pad at Cape Canaveral is being prepared for flight test. A long period of research, development, and testing is about to reach a climax. The missile, one of the most complicated vehicles ever made, is composed of more than 300,000 precision parts. It has undergone a tremendous variety of preliminary tests, and now it is being prepared for the big one. About 150 yards from the launch pad in the concrete blockhouse are the men and equipment whose job it is to launch the Atlas and monitor its performance. Each technician begins to carry out his part of the carefully rehearsed countdown. Each man is responsible for carefully monitoring a particular part of a missile. Nothing goes unnoticed. And the entire procedure is under the eyes of experts alert to detect and analyze any area of difficulty and to correct it. This flight test, the first launch of an Atlas missile, took place at Cape Canaveral on 11 June 1957. The missile rose in a stable manner, and the booster engine propulsion system operated normally during the initial part of flight. The autopilot guidance system maintained exact control, performing satisfactorily and according to plan. After 25 seconds of flight, thrust in one of the engines began to fail. The control system tried to maintain stability but could not handle the unbalanced thrust. About 3 seconds later, the first booster engine shut down, and a fire broke out in the rear section of the missile. At this point, the missile veered. It tried to recover, then fell back. After being airborne for approximately 50 seconds, the missile was deliberately destroyed by the range safety officer. Although the test might on the surface seem to be a failure, its ultimate results were extremely beneficial. Invaluable data were obtained as a result of the flight test. This information was checked and verified on captive test missiles, leading to changes in designs which were incorporated in later successful Atlas test vehicles. One of the many tools used to gather missile performance data is the motion picture camera. High-speed cameras record every important phase of flight test action. During certain Thor tests, they are placed down in the launcher itself to record details of engine performance, including the ignition sequence, thrust buildup, and liftoff. The radio guidance system has proven highly successful during flight tests of Air Force ballistic missiles from Cape Canaveral. A combination of ground-based transmitting, decoding, and receiving equipment is synchronized with airborne radio equipment to guide the missile along its planned flight path. This guidance system controls the missile through a jam-proof radio link. The bore sight camera, mounted on the tracking antenna, is loaded with film. The camera will check the extent to which the electronic tracking system performs its function. The guidance antenna and its bore sight camera automatically locks on the missile. The countdown moves closer to launch time, T-0. Countdown procedures are measured in seconds as each technician performs his role. The missile lifts off. The antenna locks onto the test vehicle and automatic tracking begins. As the missile rises, the guidance cycle is almost instantaneously in operation. In split seconds, coded signals are received from the missile, decoded, analyzed by the system's computer, compared to the pre-planned trajectory, and guidance corrections are transmitted to the missile. While the bore sight camera makes a film record of the antenna's tracking performance, other details of system performance are being monitored in the guidance station. 55 channels of guidance data are fed into magnetic tape recorders every 0.3 of a second. The duration of a flight test is short, in contrast to the countdown time that precedes the launch. Since every detail must be recorded for future study and evaluation, cameras of all types are used. One such camera is the Remote Optical Tracking Instrument, called ROTI for short, with a focal length of 500 inches. During a recent Atlas launch, the ROTI camera filmed this booster section separation approximately 68 miles from the launching site. This Thor intermediate range ballistic missile was launched to provide a further evaluation of the complete missile and to study details of nose cone reentry. The nose cone of the missile carried a capsule equipped with instruments which record reentry data and designed to be ejected a few seconds before nose cone impact. This scene shows the actual reentry of the nose cone. White hot from air friction, it drops its data capsule and streaks on in. The data capsule is equipped with devices to aid in its recovery. In this particular case, the capsule was recovered by one of the ocean range vessels a few hours after impact. After recovery, the recording device was removed from the foam plastic container of the data capsule for later analysis. A major milestone was reached in the Atlas flight test program late in 1958, when the United States Air Force achieved the first completely successful full-range flight of this intercontinental ballistic missile. Test objective of the flight was to achieve a nominal range of 5,500 nautical miles. This objective was accomplished, and all missile subsystems performed satisfactorily. Equally important milestones have been achieved in the Thor program. One such event involved the first Thor launched from its operational ground support equipment which is now installed at overseas bases. This and other succeeding launches were rated as highly successful. In line with the overall ballistic missile planning, at the very time that Thor manufacturing and testing were in progress, construction of operational bases was begun early in 1958 in the United Kingdom. Thor missiles have arrived in the United Kingdom. Thus, the Thor weapon system was an operational reality only 3 years after the beginning of the program. Construction of operational and training bases in the western part of the United States is in full swing for the ballistic missile program, as illustrated by this work going forward at Warren Air Force Base in Wyoming. Additional launch sites are being selected. The first operational and training site is Vandenberg Air Force Base. Among the facilities at Vandenberg are those for the underground launching of the Titan intercontinental ballistic missile. Complete facilities for the Atlas and Thor are being readied at Vandenberg. This Thor was the first missile to be launched from Vandenberg Air Force Base, blasting off the launch pad on 16 December 1958, officially opening the base as an active missile launching center less than 2 months after its dedication as a United States Air Force Pacific Missile Range test site. This was also the first missile to be launched by a Strategic Air Command crew. This test, the culmination of an intense effort, demonstrated that the Thor missile, ground support equipment, and Strategic Air Command crews could be coordinated to achieve a successful missile launching under operational conditions. Planning began very early in the ballistic missile program for space exploration and other scientific uses for the Air Force family of missiles. Among such specialized programs was the famous Pioneer Space Probe project, requested by the Advanced Research Projects Agency of the Department of Defense, working in cooperation with the National Aeronautics and Space Administration. A Thor served as the first stage. A modified Vanguard missile was used as the second stage. A solid rocket third stage and a fourth stage composed largely of an instrumented payload package, the Pioneer, completed the space exploration vehicles. The Pioneer Space Probe program was begun late in the spring of 1958, and at the same time a detailed launch schedule was set up. The first space probe vehicle was launched within 4 minutes of the scheduled launch time set more than 5 months before. The Pioneer payload package journeyed approximately 71,000 miles out into space and gathered important scientific data on radiation levels and of the Earth's gravitational fields in space, along with other valuable information concerning the nature of our universe. Space probe programs also permit us to gather additional flight test information relating to various future military uses of missiles. On 18 December 1958, the United States Air Force, in conjunction with the Advanced Research Projects Agency, launched Atlas 10B from Cape Canaveral. No public release of information on the objectives of this flight was made until President Dwight D. Eisenhower announced that the missile was in satellite orbit, the largest American satellite to date. Differing from other satellite launchings, the Atlas was guided under power all the way into orbit. All of the flight test objectives were realized 100%. In a dramatic demonstration of the feasibility of using an orbiting vehicle to relay messages, a pre-recorded Christmas message from President Eisenhower was beamed at the world from the Atlas. Subsequently, additional messages were relayed to and from the satellite. The successful launching and orbiting of this Atlas will undoubtedly be rated as one of the most significant events in the history of America's space exploration to date. You have seen some highlights of the Air Force ballistic missile story. The years have been few. Many calculated risks have been taken, and recently they have begun to pay off in tangible achievements which we can confidently regard as prologues of even greater achievements to come. For the ballistic missile story, there is no end, but only a series of new beginnings. Space has become our new horizon.